Hello, my name is Brock Wallen. I'm a sophomore undergraduate at Michigan State University, and today I'd like to share my research on the design and simulation of a new experimental setup to study nuclear reactions in stars. Many of the elements found in nature are formed in the cores of stars, and we want to understand the processes that drives element formation to better understand stellar environments. And this leads us to wanting to study nuclear physics and nuclear processes. Nuclear processes that occur in the core of stars drive element formation. One such process of main interest is called beta decay. Beta decay is a process that transforms one element into a different element through the emission of an electron and antineutrino from the nucleus of the element. The new element nucleus is then left in an excited state, which can de-excite through the emission of a high-energy photon called a gamma ray. So we wish to study the gamma rays emitted from the excited nucleus by measuring the gamma rays energy deposited into our detector. The electrons emitted from the beta decay process, though, interfere with our analysis by depositing additional energy into the detector. And the energy spectra on the right shows how electrons interfere with gamma ray energy spectrum, as the tail that's trailing off into the higher energies is caused by the electrons depositing their energy into our detector. And here, before we move on, I want to point out that the third gamma peak to us is the most important to our analysis, as it is the sum of the two emitted gamma rays energies. Thus, we want it to have many more counts than the first two gamma peaks. Pretty much, it needs to just have the difference that it shows here. It has to have the first two gamma peaks be low, and then that sum, that third gamma peak, have a lot higher counts. Then also included here is the decay scheme in the bottom left that shows the energy of the emitted gamma rays corresponding to the first and second gamma ray peaks. And then of course the energy at the summation gamma peak is just the sum of these two energies. So the main goal of this project is to be able to experimentally remove electron energy from the output spectrum such that only gamma ray energies remain. And to test this, new detector setups were implemented using simulations. So the first detector setup tried was the sun detector and fiber detector. Sun is the main detector and detects the gamma rays, whereas the fiber detector is what can detect electrons. Now these are actually already implemented, and you could see the actual images of these here. So now moving on to the modeling side, the fiber detector sits in the middle of sun surrounding the nuclei that are hit by the particle beam to initialize the beta decay process. So we put the sun detector on a particle accelerator such that the beam goes down the middle of it, hits the target that's directly in the center of sun, and that starts the beta decay process. The fiber detector here is split into 4 segments to detect the general direction an electron was emitted in, such that we could remove the energy the electron would have deposited in the corresponding sun segment it's traveling towards. So we do this by turning off the segment of sun the electron is traveling towards for this event, making it so sun does not read the electron's energy and does not include it in the resulting energy spectrum. The process would be repeated for every electron detected passing through the fiber detector to remove as much electron energy from the resulting energy spectrum as possible. So the results from attempting to remove electron energies from the energy spectrum using the sun and fiber detector setup didn't yield satisfactory results. First, here the blue spectra is the energy spectra without the electron energies removed, and we can see there's the clear electron tail as well as a clear difference between the first two gamma peaks and that third summation gamma peak. And then the red spectrum was the attempt at experimentally removing electrons. The electron tail is reduced, showing us that we are removing electrons, but the difference in the gamma peaks are disrupted. We have the first two gamma peaks increase significantly, while the third peak, the summation peak, decreases, and this brings them to within about 1,000 counts of each other. And really, for this red spectrum to be satisfactory, we need a clear distinction in counts between the first two gamma peaks and the third gamma peak, since we're really interested in that third gamma peak most. So while we were able to remove electrons, we thought we could do better with a different detector setup. So we decided to move on to a new detector setup that had more smaller segments to see if the large size and low number of detector segments in the fiber and sun detector setup was the reason the electron energies could not be removed while still preserving the gamma peaks. So we moved on to Sun++ and a silicon detector as the main detector setup. Here, Sun++ has 24 additional blocks placed in between the original Sun segments, which created the need for a 20-segment silicon detector in place of the previous 4-segment fiber detector. And again, this silicon detector is placed within Sun++, and it serves the same purpose as the previous fiber detector did. So the spectrum results from Sun++ and the silicon detector looked a lot better than the previous detector setup. The electron tail for the red spectra again is decreased in counts, showing that we are removing electrons again. And here, instead of having that third peak decrease, we actually had all 3 of the gamma peaks increase. This kept a difference of about 4,000 counts between those first 2 and that third peak. So this shows that the Sun++ and silicon detector setup allows us to remove these electron energies while still preserving this gamma ray peak difference. And to conclude, 2 different detector geometries were tested, Sun with the fiber detector and Sun++ with the silicon detector. Sun++ had a more promising spectrum when electrons were experimentally removed than Sun did, showing that having smaller sized and a larger number of detector segments aided to preserve the relative sizes of the gamma peaks while still allowing us to remove these electron energies. And the reason behind this is that there's a smaller probability that a gamma ray and an electron would enter the same segment in the same event in Sun++ because there were more segments, each of which were small. And this meant that removing the electron would not also remove a gamma ray as often as it happened in Sun. So with Sun++ and the silicon fiber detector, it is possible to experimentally remove electron energies from the output energy spectrum while still keeping the gamma ray peak difference and thus the gamma ray energies. And currently, right now, this project is actually being used in order to construct this new detector setup. I believe it's something with the silicon detector because Sun++ is already kind of in the process. So it's very exciting to see. And I would just like to thank these people for their help with my research project. And thank you all for listening.